All right, so topic 1.6 is our last section of the first part of this course, so Unit 1, Part 1, which has been all about change in concavity, concave up, concave down, average rate of change, and then polynomials. I know it's been fast and furious, but in Algebra 2 you had seen a lot of these functions, a lot of these words, so we're just tuning up our knowledge of these things. So in topic 1.6, we're going to discuss what's called end behavior. Now, in your previous course, you would have discussed end behavior, but probably not with the notation that I'm wanting. Since this is a pre-calculus class, we're going to use a calculus notation to talk about the end behavior of functions. But before we get there, let's just discuss what we're talking about when I say end behavior. The end behavior of a function literally describes how a function behaves at the ends. How it behaves as it moves infinitely to the right and to the left. In other words, off screen, left and right. The end behavior is what happens to the values of f of x, the outputs, we're describing the outputs, as x either increases without bound, which I'm going to use green today to talk about increasing without bound. Mathematically, with math symbols, that is going to be x approaching positive infinity. So we're increasing off screen to the right. Or we're describing how what f of x is doing as x decreases without bound, which means I am looking as x is approaching negative infinity. That's going to be the math phrases that you've seen, or that you will see. There's really only 4 options for answers when it comes to end behavior. And I'm going to give you the very basic version of each one. Let's say we have a function that looks like this. First of all, do y'all know what kind of function that is? Starts with an L. Linear, cool. If we were describing, without being super flowery with our language, so don't really use math speak to talk to me about it, what are the outputs doing on the right here? Increasing, going up, yeah? What's happening on the left? Decreasing. So in a previous course, you may have said that your end behavior is down and then up. Does that sound familiar to you? Okay, cool. We're going to do the same exact concepts, but we're going to start changing the notation we use. This is as x increases without bound. This is as x decreases without bound. Right side, left side. Increasing without bound, decreasing without bound. That's one of your options. A second option for end behavior would maybe be when a graph looks like this. Pretend that looks nicer than it does. What kind of function is this one? Starts with a Q. Yeah, quadratic. Very good. If we were describing the end behavior without fancy language, what's happening on, let's start right side again. What's happening on the right side? Increasing. What's happening on the left side? Also increasing. Interesting. So we can have end behavior where both sides go up. So as x increases without bound, f of x increases, and as x decreases without bound, f of x increases. Okay, another option, and there's plenty of different types of functions that have these end behaviors. I'm just reviewing a few of them. What if our function looked like this? Does anyone remember what this one's called? It starts with a C, but it sounds like it starts with a Q. It's cubic. Cubic starts with a C, but it sounds like a Q. Anyways, doesn't matter. If we were describing the cubic function here, what's happening on the right side? It's decreasing. What's happening on the left side? Increasing. So we can also have the opposite from that linear function, because this one is a negative cubic, fun fact, whereas x increases without bound, the outputs go down or decrease. And as we go to the left, as the inputs decrease without bound, the outputs could increase without bound. Sounds like I'm saying a lot of the same words, and you're right, which is what makes this confusing. I guess you could probably predict what's the only combination that's left? Both down. Okay, let's draw both down function, meaning that both arrows on the ends are going to be going down. We'll make it a quartic function, which is a degree 4. Kind of looks like an M. And like you guys already told me, that this could be a down, down. Because as x increases without bound, the outputs decrease. And as x decreases without bound, the outputs also decrease. Now, potentially in a previous course, this is all you may have talked about when it comes to end behavior. Concept is still the same. What I'm going to change is how we express our answer for end behavior, and we're going to use what's called limit notation. Now, you may have used limit notation last year in Algebra 2, bless you, but if you did Big Ideas Math, is that how y'all did your homework last year? Okay, the notation that Big Ideas uses is not the notation I'm using. So I will count it wrong if you write it the way that Big Ideas wrote the answer, because that is not actually correct notation. It's fine. It's not actual limit notation. And since we are pre-calculus, we're going to have to use the correct limit notation. So the way that we're going to write our end behavior for all of our left sides is with a limit statement that expresses as x decreases without bound. Notice I have that x approaching negative infinity symbol. Notice, and this is what I mean by it's different, I think in Big Ideas, you could just write it all in one sentence like flat. You have to stack it. The limit symbol goes on top of the x approaching negative infinity symbol. They're stacked. The f of x goes next to it to talk about the type of function or the name of the function you're dealing with. That might change to g of x, h of x, k of x. But then you have to tell me what it's equal to. The way you say this out loud is also different potentially. You say the limit as x approaches negative infinity of f of x is. So the limit as x approaches negative infinity of f of x is whatever the number is. Similarly, if we're talking about the right side of the end behavior, all of the green arrows, this right side end behavior is all describing the graph as x increases without bound instead of decrease. The only difference is there's no negative in front of that infinity because we're going to the right. Yes. But the same vibe. You say everything the same. The limit as x approaches infinity of f of x is, and it has to be stacked. If you write it as a line, it's wrong. It has to be stacked. We're in pre-calculus, so we write it with calculus notation. So our job in these next few problems is to not only just describe the end behavior with ups and downs, which we clearly can do from the very top of this page, but actually write the correct notation in limits and in words for these two functions. So here is the function g of x. Without using fancy language, what's happening on the right side? Down or up? Down. What's happening on the left side? Clearly, we can see what happening is for end behavior. I don't care about middle behavior, I care about end behavior. Here's how we write those answers. The limit statement would be as follows. We are doing the limit as x approaches negative infinity for g of x. Now, approaching negative infinity is the left side. What did you guys tell me was happening on the left side? Was it going up or going down? Going up. Going up. So you can either put a plus infinity or just an infinity. The plus sign is not really necessary because we know that no sign means plus, but for our notes, helpful to see the plus. We can also write the limit statement for the other side. So we'd say the limit as x approaches positive infinity for g of x this time. This time I'm talking about the right side. What's happening on that right side? It's going down, so we go down to negative infinity. This is the notation. Notation is the point of this. If we don't have the notation correct, stacked, lined up correctly, it's wrong. And I'm going to be hard about that all year long. Write my limit statements correct. Now the other thing we're going to need to be able to do is not necessarily we won't have to write the verbal limit statements for anything but my class. The test does not have it, but we need to be able to read the verbal statements for end behavior. So we're going to practice writing them because if we can write them, we can read them. The way that we would verbally talk about the left side end behavior is as follows. We would say, as the x values decrease without bound. Are y'all okay with W/O for without? Yeah. Okay, without bound, comma. The output values for this side, because we said positive infinity, we would say increase without bound. The without bound part literally is just saying goes to infinity. It's just math speak for that. So we said, translating this limit statement into the sentence, we say as the input values or x values decrease, negative infinity, the output values go to positive infinity. So increase without bound. If we change this to talk about the right side end behavior, we would say as the x values this time increase without bound, comma, what do the output values do? They decrease, very good. They decrease without bound because they go towards negative infinity. Again, being able to read the end behavior statement will help you answer questions about the end behavior statement. Did we choose the correct limit statements for h of x? Here's where we check. Is it stacked? Is the LIM above the x approaching? Did you use the correct letter for the function? The name of this function based on the problem was function h. Please make sure you used function h. Otherwise, you're talking about the wrong function. Call the functions by their names, please. If we were writing the verbal statements here, we would say as the x values decrease without bound, we're talking about as we go down, that's to the left, sorry, not down. The output values increase because we go up to positive infinity, increase without bound. That's not how you spell the word bound. For the second limit statement, to talk about as x is increase without bound, we would say as the x values increase without bound, the output values also increase without bound. Comments, questions, concerns? Make sure you got the letter right and that everything is lined up with your limit statement. Because looking at the graph is pretty easy. Let's see if we can take limit statements and translate them into functions themselves. So on the back page, example 2 has some limit statements written, and it wants us to sketch a polynomial function that could fit those behaviors. We have no information about the number of zeros. We have no information about the middle behavior, which is not a real phrase, but it's what I'm going to call the middle behavior. We just have information about the end behavior. So what I'll do is I'm just going to make sure my graph fits this end behavior. It tells me that on the left side, where should my arrow be facing as we go off to the left, up or down? Down. And on the right side, where should my arrow be facing? Also down. It tells me literally nothing else about the middle behavior, so you can connect these dots however you want. Watch the board for a second. You could do a cute little parabola. That's down, down. You could get crazy, and on the inside, you could make it a quartic function. You could have done a whole bunch of squiggles in the middle and then come back down. All we have information is about end behavior. Later, we'll start stacking zeros and end behavior together at the same time, but we're just focusing on end behavior today. So there's an option for f of x. If we're looking at g of x, where should my arrow be facing on the left side? Down. Nice. How about the right side? Up. However you connect these is up to you. I'm going to make mine kind of fun and kind of wavy. Cool. That fits the end behavior. So long as you have the correct arrows for the end, don't care about the middle, unless I gave you more information about the middle clearly. So graphs are super easy for end behavior. And in fact, not given a graph for this, it is also decently simple if you remember a few key words. If we're going to find polynomial end behavior analytically, meaning by hand, no graph, we only need two things. We only need the leading coefficient and the degree of the polynomial. Both of those things are things we've found in previous lessons. Remember, the leading coefficient is the largest exponent, or the multiplicities all added together. And the degree of, that's the degree. What are the words I'm saying? The degree is all the multiplicities added together, or the highest exponent. The leading coefficient is the coefficient of the largest term, or all of the coefficients of the factors multiplied together. And the reason you only need these two things is because the leading coefficient tells you everything you need to know about the right side. See how both of these say right side. Your right side is always determined by that leading coefficient. If the leading coefficient is greater than 0, then the function will approach positive infinity on the right side. If the leading coefficient is negative, then the right side will go to negative infinity. So your leading coefficient sign controls the right side, as if it controls your right hand. What we do after we know the right side is we look at the degree of that polynomial, because if the degree is even, then both sides go in the exact same direction. So if the right side is up, left side's up. If right side's down, left side's down. If the degree is odd, yet again odd opposite, then the end behavior is going to be opposite from the right and the left. So you can easily answer the left side end behavior just by knowing the degree of the polynomial. But we always do the right side first. Now that we've practiced, we can go look at what it would look like for an actual polynomial. So let's start by actually finding the degree and the leading coefficient. For this function, what is the degree and the leading coefficient? Degree is 5. Fabulous. So our degree is 5, which is an odd number. Almost wrote down even, is an odd number. And our leading coefficient is 4. That is larger than 0. So if you were using your body to show me this one, odd degree, leading coefficient greater than 0, your right hand should be where? Up, and your left hand should be down. That tells me exactly what I need for the right side and the left side end behavior. This is that left hand, this is your right hand, which means we will have positive infinity for the right side and negative infinity for the left side. And I know that that answers the bottom one first, then the top one. Generally speaking, I will always write them with approaching negative infinity first, and then positive infinity, but to each their own. Let's try another just to make sure we've got it. For number B, what is the degree? 4, and the leading coefficient? 1/2. Now my leading coefficient being 1/2 means again that it's a positive number. I know it's a fraction, don't care. It's a positive number. The degree is 4, which is an even number. So I can answer the left side and the right side end behavior. We'll start with the right side. Since my leading coefficient is larger than 0, I know that this is going to positive infinity. And since the degree is even, is the left side the same or opposite? Same, so it's also going to positive infinity. The right side end behavior, since the leading coefficient is negative, would go to negative infinity, would approach negative infinity. And since this is even, the right side, left side end behavior has to be the same. If we look at question D, what's the degree here? 5, which is an odd number. What's the leading coefficient? It's actually not 3. -1. It has to be the coefficient of the term with the exponent if it's written in standard form, which this is out of order, but not multiplied form. So our leading coefficient here is actually -1. Since that's less than 0, that means that the right side is going towards negative infinity. An opposite, odd opposite, means that the left side is going to positive infinity. Again, you can put the plus in front of that infinity. That's totally fine. For letter K, This one has a similar, quote, trick to it. What's the degree? 5, which is an odd number. And so what is my leading coefficient? -1, which is less than 0. Yeah, we're always talking about the coefficient of the leading term if it's multiplied out. So negative leading coefficient means that the right side as x approaches positive infinity is negative. Odd opposite goes to positive infinity. Now this last one, if you attempted it, I'm so happy that you attempted it. There's a total possibility that we were wrong, and that's okay. That's what notes are for. Why do you think I'm saying this one is a little bit more tricky? It has no degrees showing. Yeah, it's in factored form. It's not written out in standard form like the rest of them where we can see all the cute little powers. So we have to think about multiplicities for a second. If we were to add up all of the multiplicities of these zeros, this has a multiplicity of 1, this has a multiplicity of 1, and this has a multiplicity of 1. Which means what's my degree? 3. Very good. See how things come back? So this one has a degree 3, which yes is an odd number. The hardest part of this question though is the leading coefficient. I'm going to tell you what the leading coefficient is, and I want you to tell me why. The leading coefficient here is -2. What? How is that possible? What's the coefficient in front of the first x? 2, right? What's the coefficient of the second x? 1. What's the coefficient of the third x? -1. 2 times 1 times -1 would make -2. That's my leading coefficient. So when the problem has multiplicities that you have to add together, pause on the leading coefficient and make sure you're actually multiplying those numbers out. So again, if we want to write this down in our notes, just to make sure we remember why, put a little arrow here and say this was 2 times 1 times -1. Those were the leading coefficients from each term multiplied together. And we added the multiplicities. I guess we could show our work here. 1 plus 1 plus 1. Well, now that we know this, and we've got the leading coefficient and the degree situated, since that leading coefficient is negative, I know that as x approaches positive infinity for m of x, the outputs are going down to negative infinity. And the degree being odd means that as x approaches negative infinity, or as the inputs decrease at outbound, that is a really good infinity sign. I'm very proud of that one. Sometimes mine look like janky 8s, but that one actually looks pretty good. Very proud of me.